honor for me to be here. I would say one of the main ways that Ian and David have influenced me is through the Golden-Jackson cluster method, which I've used many times to count permutations, avoiding consecutive patterns, or according to the number of occurrences of consecutive patterns. Now, I'm not going to talk about that today because some of you have already heard me talk about permutations and consecutive patterns. So instead, I want to talk about something new that maybe nobody here has heard. I'm not sure. Also, I realized Ira is giving a talk about the Golden-Jackson method this afternoon, so that's perfect. So my talk will be about lattice paths, and we'll be counting very simple lattice paths. So this will be just lattice paths with two kinds of steps, like up and down. Except the twist will be that we'll be counting them according to some statistics, which will make the problem harder, but then still the formulas that we get at the end are going to be pretty simple. So let me give you just an overview. So this will be just paths with two kinds of steps, and then one of the statistics will be the number of crossings. Now, the number of crossings will be defined in two different ways because there will be two kinds of problems. One will be about single paths crossing a line, and the other will be pairs of paths crossing each other. But essentially, the number of crossings is what you think it is. And that has been studied. That statistic has been studied at least since the 60s. There are some papers about counting lattice paths with two kinds of steps according to the number of times they cross a line. And there's, of course, in the case that you have tuples of paths with no crossings, that's also been studied, and it's counted by the Lindstrom-Gesell-Viennow determinant, which is the third talk in a row where that is mentioned. And then there's another kind of statistic that's very different from the number of crossings, and it has also been mentioned at Terry's talk yesterday. So this is the number of valleys or descents of the path, and the measure index, which is just the sum of the positions of those descents. And this statistic was introduced by McMahon because you can think of the path as a binary word, and then this is just the usual descent and measure index. Okay, but the interesting part will be combining these two kinds of statistics. So the crossings on one hand, and the measure index and descent on the other hand. Okay, so now let's get a little bit more precise. So the first problem I will study is about paths crossing a line. And this is the kinds of paths that I'll be looking at. So it's just paths with up and down steps. So this is even easier than dig paths because there's no requirement about not going under the x-axis. So this just, the number of these paths is a binomial coefficient. So they have steps up and down. And the statistics I'm defining, so one is the number of descents, which is just a descent will just be a valley. So it's a d followed by a u. And then the other statistic is the measure index, which is the sum of the positions of the descents. So you can think of that as this. So in this path here, there are 4 valleys, and they're in positions 1, 3, 7, and 10. So when you add those, you get the measure index of this path. Okay. Another thing I need to define, and this also appeared in several talks. I think George Andrews already mentioned the Q-binomial coefficients. So this is just a refinement of the binomial coefficients with a parameter Q that when you set it to 1, you just get the usual binomial coefficients. And it's well known that if you count those lattice paths with, so G, A, B are paths with A up steps and B down steps, according to the measure index, then you just get this Q-binomial coefficient. So this is the same as counting binary words according to the measure index. And this is one of the interpretations of the Q-binomial coefficients. Okay, and here's a quick example. So if you have 3 up steps and 2 down steps, you just get this binomial coefficient, 5 choose 3, which is this polynomial. Okay, so it's known that you can also refine this by the number of descents. And then if you take the same paths, but now you have 2 variables, one keeping track of descents and the other keeping track of the measure index, then you get this formula, which is still quite nice. So this is a So even though this looks like an infinite sum, but it's really a finite sum because when n gets large enough, these are 0. So this is a polynomial in T and Q, whose coefficients as a polynomial in T are these products of Q binomial coefficients. And here's an example for the same paths as before. You get this polynomial in T and Q. Okay, so this is one type of statistic. The other will be the number of crossings. So let me tell you what I mean by that. So for this single path, what I will have is a horizontal line. For example, here the line is y equals 1. In general, this will be y equals L for some integer L. And I will define this. I mean, the notation is not the best, but this is the set of paths with A up steps and B down steps that cross the line y equals L at least r times. The reason for the at least is that it will make the formulas better. If you want exactly r, you can just subtract at least r minus at least r plus 1. Okay, so this path here is crossing the line y equals 1 3 times, and I've circled the crossings. In particular, if you set this r equal to 0, these would just be paths that cross a certain line at least 0 times, so that's all the paths. Okay, so I'm interested in these polynomials that count these paths according to the number of descents and the measure index. So the goal will be to give you some formulas for these polynomials. And now the formulas, for purposes of this talk, the formulas will be easier if I get rid of the t. So many of the formulas I'll give you just have t equals 1, but there are generalizations adding a variable t, but they're just a little bit too big to fit on the board. So most of them, I'm just going to be giving you the case t equals 1. Okay, so this is the first theorem. So here's when the line being crossed is the x-axis. So that's the line y equals 0. And this is the formula that we get. So if you count paths with A up steps and B down steps that cross the x-axis at least r times according to the measure index, turns out you always get these nice Q binomial coefficients multiplied by some power of Q. In the case where the path also ends on the x-axis, that's when A equals B, you get this extra factor. But essentially, these formulas are surprisingly simple. So when I saw this, I was pretty surprised that the formula would be so simple. Now, there is the way we prove it is bijectively. But let me tell you a little bit of what was known before. So if you ignore the descents and the measure index, so that's setting t and q equals to 1, this has been studied in the 60s in the probability and statistics literature. And then it has been rediscovered by other people who didn't know it had been studied in the 60s. Now, the proofs in that case are essentially obtained by applying the reflection principle multiple times. So every time you have a crossing, you can sort of reflect the appropriate piece of the path and then keep removing the crossings and then get to something that you can count. Now, unfortunately, that proof does not prove that argument doesn't prove the version with the measure index, because when you reflect a piece of the path, you don't know what happens to your measure index, and that doesn't prove the theorem I wrote. There's another connection with an existing paper. If you ignore the descents, the formula I had appeared in a paper by Seo and Yi about counting certain ballot paths with marked returns in another statistic. So these are slightly different paths with a slightly different statistic, but they give the same formula. And there's a way to prove that these are really the same problem. Now, the proof that they give is by induction, and it doesn't give a bijection. So the proof I'll show you is using a bijection. And then there's also a connection of this result to some work I'm doing with Sylvie Cortel and Carla Savage, where we count partitions according to, with some restrictions on the ranks of the partition. So there's a way to go from partitions to paths And then these results about crossing a line and about measure index, they have interpretations for partitions. Okay, so that was the result I showed you first was when the line being crossed is the x-axis. If the line being crossed is not the x-axis, so the line was y equals L, and now L is any integer that wasn't covered by the previous theorem, the formulas are still just as nice. So there are different cases according to whether the line is, so the starting point is below or above or on the line, and if the final point is above, below, or on the line. So each case has to be dealt with a little bit differently. So that's why the theorem looks so long, but essentially all the formulas end up being the same. So, and then the parity plays a role because so this first case would be the starting point is below the line and the final point is above the line. So then the number of crossings is going to be odd. So that's why crossing 2m times is the same as crossing 2n plus 1 times. But and then if the initial, well, depending on the parities, you get different things, but all the formulas end up looking very similar. And then when the final point is on the line, then you get different cases for even and odd, but they all look like a Q binomial coefficient times the power of Q. Okay, so I'll tell you something about the proofs later, but before that, let me tell you the second type of theorem that we get. So this is about pairs of paths. So instead of having one path and counting how many times it crosses a line, you can look at pairs of paths and count how many times they cross each other. Now for this part, I'm going to draw the path tilted 45 degrees because it makes the notation a little bit easier. So sorry about changing it in the middle of the talk, but so now the paths will have steps north and east, but all the definitions are the same as before. So descents are just now corners east north, and then measure index is just the sum of the positions of those descents. So it's really the same definition as before. And I'm going to use this notation. P A arrow B is the set of paths that start at A and end at B. Okay, so the same formula, McMahon's formula that I wrote before, if you write it in terms of paths from A to B, it just looks like this because this is the number of east steps and this is the number of north steps. Okay, so now let me define what the crossing is in this setting because now I have to be a little bit careful about what the crossing is. When you had just the path crossing a line, it was obvious what the crossing would be. Now here, so something like this, so if these are the two paths, something like this is a crossing, something like this is also a crossing. So basically, for it to be a crossing, you need the paths need to get to a common point from different directions. They could be together for a while, but when they separate, they have to go in the opposite. If one came from above and the other from below, when they separate, they have to go in the opposite directions. Like here, the red one was coming from below, and then it continued going above, and so that's why this is a crossing, but this is not. Okay, so this is how we define crossings, and then there's this notation I'm going to use. So this is a set of this is the pairs of paths where the first path goes from A1 to B circle, and the second path goes from A2 to B filled circle, and they cross at least R times. Here's the circle. This is just so because I didn't want to write 1 and 2 because then sometimes it will be 1 and 2 and sometimes it will be 2 and 1. So that's why I have these weird symbols. So, okay, so this is the set of paths I'm interested in, paths that cross each other at least R times. Here's an example. So the red path goes from A1 to B2, and the blue path goes from A2 to B1. And they cross, these ones happen to cross exactly 3 times. And I've circled the crossings. Okay, so we want to enumerate these with respect to the number of descents and the measure index. Now, the way we'll do this, the number of descents will really be the sum of the number of descents in the two paths, and same for the measure index. I'm not able to keep track of the individual number of descents of each path, but so the polynomials we'll be interested in are these ones. So this is the sum over all pairs of paths that cross at least R times, and then T keeps track of the total number of descents, and Q keeps track of the total measure index. And then as before, we have formulas for arbitrary, so with these parameters t and q, but I'm going to show you the formula when t equals 1 because it looks a little bit simpler. Okay, so let's start with an easy case. So the easy case would be if I don't have any restriction about crossings. So this would be the polynomial that counts pairs of paths with at least 0 crossings. But if there's no restriction about crossings, I can just count each path separately. So this is counting path, the first path, the one that goes from A1 to B circle, and this is counting the paths that go from A2 to B filled circle. So this is just the formula looks very easy in that case. But what I'll show you is that when here you put an R, when you require the number of crossings to be at least something, the formula still looks very much like this. So the way it will look, it's essentially like this. So I'm defining this formula so I don't have to keep writing this every time in the theorem. But this is essentially a product of two q binomial coefficients and a power of q. And now I can state the theorem, and there will be this other notation I'll use. So A1 less than A2 means that the point A1 is strictly northwest of A2. Okay, so this is the main theorem for pairs of paths. So you have the two initial points, A1 and A2, and the two final points, B1 and B2. And A1 is strictly northwest of A2, and B1 is strictly northwest of B2. Now, for this theorem, I need a requirement that A1 and have to be on the same line of slope -1, because if that's not true, the measure index doesn't work well. Because essentially, I want to count the way I count the positions of the descents. I have to start counting from sort of the same place. That's why I need that. Okay, so the theorem looks like this. If I count pairs of paths from A1 to B2, the first one goes from A1 to B2, and the second one goes from A2 to B1 with at least 2m crossings, which is the same as at least 2m plus 1 crossings because the number has to be odd. Then I get that formula from the previous slide. So this is where this definition, this f was this. So I get that the polynomial that counts these pairs of paths is given by this nice formula. And then the same is true if I have the endpoints switched, only that now the number of crossings has to be even. So these two things are equal. And then there are variations where you have the same initial point. So when the two paths start at the same point, let me call that A. And if the two paths end at the same point, let me call that B. You still get the same kind of formula. So they are all in terms of this function f. So this is when the initial points are the same. This is when the final points are the same. And this is when both the initial and the final points are the same. This actually gives the more complicated case of all of them, because now it's no longer just a product of q binomial coefficients. You have to do some alternating sum. Okay, so these are the theorems. Let me tell you a little bit more. So if I don't care about the measure index and the number of descents, then I could remove that requirement that the initial points have to be on the same line of slope -1. And that could be proved in the case where I don't care about measure index and descents. That could be proved similarly to the usual proof of the Lindström-Gesell-Vienno determinant by swapping the prefixes of the paths until the first time they cross. There's something like that you can use to prove it if you don't care about the measure index and the number of descents. Now, unfortunately, when you care about the measure index, this proof wouldn't work because when you swap the prefixes, you don't know what's happening to the measure index. So we need a different proof. So I'm going to show you a little bit how that other proof goes. So the proof I'll show you works for the measure index. It still doesn't work for the number of descents. If you also want the number of descents, then you have to give a different bijection, which is more complicated because it uses some other object that Kragenthaler had used called two-row arrays. And I'm not going to show you that today, but it's still a bijective proof if you have both measure index and descent. Now, the two-row arrays, by the way, those were used. So Kreinenthaler has a refinement of the Lindstrom-Getzel-Viennot lemma that keeps track of the measure index. And it actually looks a lot like the determinant for counting paths, but you can substitute the binomial coefficients with Q binomial coefficients and put some powers of Q, and then it also keeps track of measure index. So I didn't know about that until I started working on it. So I was surprised that that's not like more famous. It's a pretty nice, it's a very nice refinement. Okay, so that proof uses two-row arrays, and those are the ones that we need to do our refinement by descent and measure index. Okay, so let me tell you a little bit about the bijections. So the bijections are based on some very simple bijections that I'm going to mention here. So if I take paths that end with an E step, I'm going to put this E to mean paths from A to B that end with an E step, and these are paths from A to B that end with a north step. Then there is a bijection between the paths that end with an E step, so paths from A to B that end with an E step, and paths that start a little bit below and to the right of A. So V is this vector 1, -1. So if you start at A plus V and you go from that point to B, ending with a north step, then you can construct an easy bijection from here to here. And basically all you do is take the east-north corners of the black path and make those the northeast corners of the other path. And it's easy to see that these corners uniquely determine. So this is a bijection. And it's also easy to track the measure index when you do this. So it's not preserved, but it changes predictably. The inverse is just a bijection that takes a path from A to B, and then it gets a path from A minus V to B that has the corners in the same places, but the corners go in the opposite direction. And of course, the measure index changes predictably. So using those bijections, now I can construct the bijection that proves the main theorem in the following way. So I'm going to do an example here. So there's a pair of paths. The P goes from A1 to B2, Q goes from A2 to B1, and these ones have at least 2 crossings. I mean, they happen to have 3, but I'm going to take, for the example, I'm going to take R equals 2. So now I look at the rth crossing from the right, which in this case is the second crossing from the right, is this C. And I look at the prefixes up to that crossing. So now the prefix of P up to that crossing ends with a north step. The prefix of Q up to that crossing ends with a east step. And I'm going to apply those bijections I just showed you to those prefixes. So for example, this prefix of Q has a corner here. So I'm looking at this east-north corner of Q, and I will turn it, when I apply the bijection, into this piece here that has a northeast corner at the same point. And then the prefix of P had a northeast corner here, and that's going to become the east-north corner of when I apply the bijection. So I'm applying those bijection to the prefixes, and then I get a pair of paths. And by doing that, I can keep, well, with the right setup, this is a bijection, and I can keep track of how the measure index is changing, the sum of the measure indices. Now, I can repeat that, but now instead of taking the second crossing from the right, I take the last crossing from the right, and I get a composition of bijections. And each time I apply one of these bijections, I know how the measure index is changing. And at the end, so in this case, I would apply the bijection to the second crossing, then to the first crossing. And what I end up at the end is going to be a pair of paths with no restrictions about crossings. And those we can count, because now these are just arbitrary pairs of paths from a certain initial point that's different from the one before and a certain final point. So we end up getting this bijection between paths that have at least 2 crossings and paths that have at least 0 crossings. And as I said, we know how the measure index changes, so then that basically gives the proof. So when we want to count these paths here. This is just a product of q binomial coefficients, and then there's a power of q because of the way the measure index has changed when I apply the bijection. Okay, so let me, yeah, there's another application of these bijections I showed you. They can actually be used to give I think it's a slightly simpler proof of Combinatorial refinement by the measure index of the Lindstrom-Getzel-Viennow determinant. So if you only care about the measure index and not the number of descents, then you can, instead of the proof that he gives through these two-row arrays that don't correspond to paths, you can just modify the paths themselves using these bijections, and it gives you a proof that's at least easier to follow what the bijections do. Okay, for the other problem I talked at the beginning about paths crossing a horizontal line, the bijections that we use are related. So they look a little different here, but essentially this is what they do. So here you have a path P, and you can, this is a path P that ends with a down step. You can apply a bijection that I call tau that is defined in the following way. So you take all the valleys and you reflect the positions of those valleys along the x-axis. So you're going to get valleys in these other positions, and there's a unique path. Well, there's some extra conditions about the starting point that I'm not mentioning, but with the right setup, this is a bijection. And similarly, there's another bijection sigma that reflects the peaks. So if you have a path P, you look at where the peaks are, and now you reflect them along the x-axis, and that will determine another path. So these bijections, tau and sigma, the first one preserves the measure index because it hasn't moved the horizontal position of the valleys. The second one doesn't preserve the measure index, but we can track how it changes. And by combining these bijections, we can prove the theorem I wrote at the beginning with paths crossing a horizontal line. So this is how the proof would work for paths. So let's say I want to count paths with 8 up steps and 6 down steps that cross the line y = 1 at least twice. So the first thing I would do is move the path down so that the line being crossed is the x-axis, and then I will, because this the number of crossings is at least 2, it would be 2. I look at the second crossing from the right. I take this prefix and I apply the bijection tau that reflects the positions of the valleys. And now I would take the prefix of this new path all the way up to the crossing C1 and apply the bijection sigma, reflecting all the peaks. And now the composition of these bijections takes me from this black path to this magenta path. And this magenta path has no restriction on crossing. So it's just an arbitrary path with in this case, a + 2 up steps and b - 2 down steps. And we can count those. Those are very easy to count by measure index. So that's how we do the proof. Okay, about the refinement. So all these proofs I've shown you and these theorems didn't have the variable t. So I'm just going to say, I just have a slide about what happens when you incorporate t. So if you also want to keep track of the number of descents, the formulas look more like this. So this would be paths with a up steps and b down steps that cross the line y = L until at least 2m times. And then t keeps track of the number of descents. So they look a lot like the formula I showed at the beginning where there were no crossings, but now I keep track of crossings, and it still looks like a polynomial in t where the coefficients are q binomial coefficients and powers of q. So that's how this one looks. If you count pairs of paths, it looks a little worse, but not too bad. So this would be a sample formula when you have initial points a1, a2, b1, b2, and the initial points are in the same line with slope -1. If you want the polynomial that counts pairs of paths with at least 2m crossings with the 2 variables, keeping track of descent and measure index, then you're not going to get just binomial coefficients, but you're going to get this product of two polynomials where each polynomial has very nice coefficients. Okay, now when you add the descents, this proof I was showing you with these nice bijections that just move peaks and valleys around, those don't work because even though they change the major index predictably, they don't change the number of descents predictably. So that here's where we need this other trick of using Prandtl-Thaller's two-row arrays. And I'm not going to say anything about those, but okay, I'll say one sentence. So that they basically encode the positions of peaks and valleys, but they're more general than paths because you could have the two rows of this array could have different lengths, and in that case, they don't come from a path anymore. Okay, this is all I had. Thank you very much.
Are there any questions for Sergi? Yeah, go ahead, Joel.
Put in -1 for some of the variables. Does anything interesting happen?
Okay, so the question is, if I put -1 for some of the variables, does anything interesting happen? So I guess the Q would be the natural candidate, but I don't know. I haven't looked at that. So I'm not sure. So even I guess what do you know what happens in the original formulas without crossings? No, okay, because I guess that would be one place to start. I haven't. Yeah, I don't know what happens. Yes.
So you're saying that you exchange the major when you try to get something without when exchange there's a problem with the major index, but is there also a problem with T with the descents or?
Okay, so the question is when I try to prove the Gessel-Viennow determinant, is that what you're saying?
Yes, it doesn't preserve it.
Wait. So you're asking about the proof of the refined Gessel-Viennow?
So at some point you mentioned that the switching fails, but for Q, but I was wondering if it also fails for T.
So you're thinking about this. Yeah. I see. So you're looking at the easy. So Alejandro is asking in the easier here when I was saying that the case where we don't care about T or Q. So this would be counting pairs of paths according to the number of crossings, and that can be proved using the Lindstrom-Gessel. Well, the same idea of switching prefixes. That messes up I'm pretty sure that also messes up the number of descents, not just the major index. Actually, I don't know if I looked into that specific question of just keeping track of descents, but not major index. First I found the formulas for the major index, and then I realized you could refine with descent. So I didn't try the other way, but I'm pretty sure it would also mess it up. But it's a good question.
Any other questions? All right, let's thank Sergi again.